Good evening, everyone. Folks that are, yeah, let me actually pull this up here. Good evening, everyone. Welcome to our January location here at Rice University, Thursday, January 8th, 2026. Got to get used to saying that new year. So welcome to folks who are online. And so this is real exciting that we get to interact with Brad and Austin and Sebastian tonight. And we'll have a lot of fun talking with them. So did you want to call up the startup page, Colin? All right. So we'll just give you some basic info about the club and such here to start with. So, of course, we are the Houston chapter of the organization that has chapters all across the US and Canada. And we've been going around for a long time, having a lot of excitement as electric vehicles have developed. And of course, we say vehicles nowadays because we are excited about electric airplanes, electric motorcycles, electric boats, all kinds of good things. And so I've got a few slides here just talking about opportunities here with our Houston chapter. All right, so we got it full screen for folks that are online on the Zoom call. And folks on Zoom, if you want to put questions in the chat, you can do that when we have our speakers going. So last month, we had a lot of fun at our December social, and we'll do that again here coming in December of 2026. So folks that like to plan ahead. This was over at the Katz's Deli on Westheimer, the one that's called the Galleria Katz's Deli. And you can see some of the faces there in the photos that you see of the folks here in the room. So we always encourage folks to bring family members. That's always a good thing. Okay, next one, Colin. And past events, so some of the fun vehicles, you can see a classic Tesla Roadster on the right there in orange. And it's really fun. Folks have started painting words onto Cybertrucks now.
An event to raise money for some foster kids in Montgomery County.
Mhm.
So Tesla invited us out.
So great that we could participate in that. And we try to do different events. We'll see if we do the Botanical Garden again this spring or not. And I was already talking with Brad about other possibilities, an April event that you'll probably mention. For folks on the south side this month, it will be, well, it says January 9th, but actually it's January 16th. So not tomorrow. It's a week from tomorrow. Emma didn't want it to be too close. But for folks that are on the south side of town, the J stands for the JSC for Johnson Space Center, Electric Vehicle Enthusiast Club. And so everyone is welcome. We just do that as an event on that side of town. You'll see another event on another side of town coming up. So Batteries and Brews, we've got that coming up on Sunday, January 25th, starting at 1 in the afternoon. It's out west at the Watershed, which is in a nice strip shopping center out there. It's on West Belfort. And we don't do any kind of program there. We just all meet up together and exchange ideas. So everybody's welcome to come to that. Everyone's on their own as far as any food or brews or other beverages. Okay. And we have the art car parade. So David Lowy is getting involved with that. He's our club vice president. And as you can see, he's created this is not actual images on his car. He just put them on electronically.
Well, yeah, and he's trying to do it non-destructively.
Right, exactly. So he's going to see what kind of maybe things he could stick on that can come off without taking the paint.
Contact us if you were interested.
Right, exactly. So this will be the first time that we really get involved with the art car parade, but it sounds like it'll be a lot of fun. So robots at Amazon tour. So some folks may have seen, whoops, our big screen went out. Sort of lose connection. But I'll keep going for the folks online. In the email that went out, it talked about how the Amazon folks offer a opportunity to see how they use robotics in their facility. And so you can just respond to the email, to the club email, and it will get collected up, and we will pick some dates, and we'll see what reset timer. The screen times out. Okay. So that's what it means by robots at the Amazon tour. Okay. Of course, there's a lot of benefits. If someone wants to join the National EVA group, you can read some of them there on the screen. Okay. And we have here in the room EV1 sheets. We get them from the national organization, and they age very quickly because the number of vehicles out on the market change a lot. But if you've got some friends and neighbors who are EV curious, you can take some of those and hand them out. We also have new business cards that have QR codes on them to help folks get to information quickly. And here's just another listing of the opportunities with the Art Car Parade. Anyone who knows a lot about Instagram, we'd be happy to have you help get some things. We do put certain information out on Facebook so people can find us there. And of course, presenting a topic, we're always looking for folks that want to share their knowledge. And who knows, we may do an EV trivia night at some point. And some other opportunities. Consumer Reports is asking for some input, specifically about charging. So you can contact the national organization at myev.org at the link at the bottom there. And here's the Facebook reference and just some sample questions out there.
Somebody is buying BYDs in Mexico and driving them across the border.
Besides just like a rental car temporarily across, they're actually bringing them across and they're staying?
That's what we're talking about on Facebook. It may not be true, but
okay,
we're talking about it.
Okay. Well, and over the years, I see a Mexican license plate every once in a while. I mean, it's not uncommon for somebody with a car in Mexico to, drive it across on a vacation or something like that. But 2,500 miles a year is interesting. Okay. Well, I did see a headline yesterday. It said that one of the Chinese companies, Geely, is actually aiming to have their cars legally for sale within 3 years in the US. So we'll see. Of course, we know that Mexico's got a lot and Europe is getting a lot. Yeah, when I was in France recently, you drive down the highway and you see the Xpeng and you see the BYD dealerships there just along with the other brands. So normally, of course, next month, we will be back at TXRX. So our usual location. So all the folks, tell all the Rice students, please come next month if they can in person. If not, Zoom is always good. And that's it for what I wanted to cover at the beginning here. So Brad, if you're ready, I'll hand the mic over to you. And we'll find out all the exciting stuff that's going on here at Rice.
Sounds good to me. Let's get started. That should be working. Well, hello, everyone. My name is Brad Mahung. I'm a junior mechanical engineer here at Rice University. And this past fall semester, I took upon the project of restoring Rice's first ever electric vehicle, specifically the E-Van. So to give you a little bit more context about its history, kind of where it came from, we have this short video for you to watch.
So we are getting in a 1997 Chevrolet P30. At least on paper, that's what it is. But this is an old housing and dining bread truck that we 30 engineering students converted to electric power over the course of last semester and this semester. Hold the power button down, take your RFID card, put it up against the dash. Comes to life.
I was sitting with Austin in class last spring, and he was saying what we want to do for senior design, and he was like, I want to work on a vehicle, because he's a big car guy. And he said housing and dining has a van, and they want it to be converted. I was like, I'll help with that. I don't know anything about vehicles, but I just said yes.
And at the request of the sustainability department and housing and dining, we took this truck, stripped the old powertrain out of it, and did an electric conversion on it. Took us about 6 months to do, and we started in the fall of last year, and it's running and driving right now. It will be at Showcase, and it has about a 100-mile range on the highway and 225-ish in the city, because it is a brick on the highway. but it will be used for kind of the campus purposes by Housing and Dining to take food and dorm furniture and those sorts of things around campus wherever they need it to go.
Some of the parts were off the shelf. Some of the parts were basically given to us by our sponsor at Omni Powertrain. They said, "Hey, we're interested in this project. We would like you to use some of our parts and give us feedback on how they're going."
During my first semester in freshman year, I didn't expect to be involved with, a senior design project, much less something as cool and advanced as the EVA. Getting to work on this has been one of the highlights of my year. I had a lot of fun working on it, and it's been a great learning experience.
Now, when you come to Rice, you expect to have a holistic experience. You expect to have the classes, you expect to have a place like the ODEC where you can build cool stuff, and you expect to have the cool stuff to build. This project has certainly fulfilled all three. We've taken classroom knowledge, we've built it on campus, and we've built something for campus that students are interested in. For me, it rounded out my Rice experience and was kind of the cherry on top that I was looking for and that a lot of other people were looking for as well.
So with that short video, there are a few things that were left out. So this project, as they said, was completely student done and was built here in the ODEC. So for those of you who don't know, this used to be an old kitchen for Rice, and they converted it into what you see today with all these different tools, equipment, and space for us to work on projects like this. And the original project was extremely interdisciplinary. So there were mechanical engineers, electrical engineers, all working in unison to get this thing done in about 6 months or 1 school year. So some of the technical information about this van, it's kind of cut off there. No worries. So this van can get 100 miles on the highway. Like we said, it's a brick, it's a giant box, so not that efficient, or 225 in the city. It is using an Omni Powertrain M24P0D motor. So this motor is actually double stacked. So there's 2 motors coupled together. This makes about 500 horsepower at peak performance and 650 foot-pounds of torque. So I still remember the first time Austin took me on a ride in this thing my freshman year. It pulls. I mean, this thing is quick. And it is a 3-phase permanent magnet synchronous motor and was actually donated by the company. So Omni literally said, here, we have this experimental motor we're trying to develop for electric vehicles. We know you guys have this project. Just take it and see what you can do with it. So that's how we ended up getting that motor. Now, the battery pack that we're using is a Tesla P100D battery pack and is operating with 400 volt architecture. So we have an example of one of the modules there. There are 16 individual modules split between 3, or in the original design, 3 battery boxes. And each module helps us get to that goal of 100 kilowatt hours when fully charged. And lastly, to control all this electronics and keep things safe and fully charged, we have the Orion BMS. This monitors the health of the battery pack. It ensures that we get good, even charge between all the modules and provides data actually directly to the vehicle's dashboard so we can see the health of the modules just from that itself. And also allows us to get good information just using a normal, I think it's a CAN sensor or OBD port. So that's another great plus from here. Yes, sir. I don't really know how we got the pack. One of the speakers later, his name is Austin Greer. He was the guy who came up with this whole thing. I came in a little bit later because the project came in a little bit of disrepair, but there are a lot of things that he knows that are specific to this project. So you'll hear from him soon. So with the original battery box design, there was 1 pack in the front that housed 6 modules. So you can kind of see the box there. I wasn't able to get good pictures of it, but it was 6 stacked in 3 and 3. And then behind the driver and passenger, there were 2 additional battery module packs. So they're stacked 5 and 5. So these frames are made out of aluminum extrusions to keep it lightweight. And the shells of the actual boxes are made from 22 gauge sheet metal. And that's how they designed the original modules. Now, the next innovation they had was with the original thermal system. So what you see there is a sketchup of the original design. This design incorporates everything as one single loop. So you go from the batteries straight to your inverters or motors. And it actually is fairly mechanically simple. There are no valves or, yes. We'll get to that soon. So a lot of your questions I'll get to after the initial design step here. Anyway, so you can see the design there, very mechanically simple, just two pumps that control the pressure in the system, and it's actually connected also to the cabin. This is utilizing the original radiator, which is a big deal, helps save a lot of costs for the project. And as I mentioned, it's very cost effective. Less moving parts means less things have a break with time, keeps things simple. So with all that being said, all this great engineering, the van does have some issues. Now, keep in mind, again, a lot of us students here, we've never done something like this before. So of course, there's going to be a little bit of engineering oversight. And one of the biggest things that we noticed was that the drivetrain actually had pretty severe vibrations over about 60 miles an hour. And what I have pictured here is the typical drive line for a truck that you would see in a modern day vehicle. So you go from a transmission to a front working angle, the front prop shaft, which is supported by a center support, and so on and so forth. Now, I have a picture here. It's not the greatest, but there are, as you can see, some differences between what you're supposed to have and what's in the E-van. So in the E-van, you go from your motor's gearbox directly into a solid axle, which then connects to your middle working angle and then is directly coupled to your rear prop shaft. So what's missing is actually both your front working angle and your center support. Now, they caught this later after testing and they tried to resolve some of the issues, but because of the timeline, they weren't actually able to fix this in time for delivery to housing and dining. But this is a pretty glaring issue to have in a drivetrain, especially when you plan on taking on the highway. So for now, it's been restrained to just campus use because below about 40 miles an hour, you're not going to see these issues. But one of the future goals is definitely to fix this issue here. Now, where I came in was with the battery frame. And unfortunately, because of the aluminum construction and the way that they did it, it did end up collapsing. So it's important to keep in mind that each one of these modules weighs 60 pounds dry and weighs even more with liquid in it. And in the original design, as you can see, there's no horizontal support. It's only supported vertically. So there's nothing keeping it from buckling to the sides. And the other thing to note here was that they use these friction fit joints to sort of keep everything together, which is smart. It's a very good way of building originally, but it obviously didn't stand the test of time. What I think may have happened is that they may have driven over a speed bump a little too hard or a pothole, as you know, in Houston, probably driving here, these roads are not the greatest. And as you can see, what has happened is that the frame, this is one I had to rebuild. Even when I try to get it straight, you can still see that wall is slightly arched out. And because these battery modules are hanging on by a piece of plastic about 1/4 inch thick in the actual rail slot, the moment that gets loose, you see that these modules just collapse in on one another. And that's what caused the van to be in a state of disrepair when I found it. And that's what Austin and I spent the better part of this semester trying to figure out how to solve, is how do we protect these modules from this sort of damage? So the goal was to design a robust, user-friendly, and easy to maintain, or at least easier to maintain, battery box for the E-van. So what did we actually do? The objectives were to arrange the rear 10 modules that were in those original 5 stacked configuration into a single flat layer, which is more common for EVs, as you know, in the industry. It also to create a way to disconnect the high voltage lines between the front and rear packs. So in the original design, there was no switch or cutoff. You literally had to go in with a wrench and just unbolt it. So that's how you would take it down step by step from 360 all the way down to your last pack, which was fun to say the least. So now we're going to do something about that. And also, of course, increasing the vibration damping in the system, especially in the pack itself. Next, to weatherproof the box and protect the modules from water and other debris, especially since this will be a work truck. So these guys will be just hauling anything and everything in the back of this truck. We want to make sure nothing gets damaged. And also better insulate the HV lines or high voltage lines and prevent any sort of short circuiting. That's just an obvious one. And lastly, with the original thermal system, there were some issues where because the motors was applying a lot of heat into the original system, you can get that heat back into the batteries. So testing to see how efficient the system is and seeing what kind of improvements we can make in the future. So this is the revised battery layout. On your left, you can see the original design of the 5 stacked right there. And then my design is on the right here with the flat layout. So underneath that shell is actually the new configuration. This is the best I could do with the space we had in the back of the van. So to answer your question, the reason why we can't do all 16 modules is because the back portion of the van can only fit about 4 more modules, meaning we would have 2 loose ones just kind of sitting around somewhere. So the best we could do was to leave 6 in the front of the engine and then place the back 10 in the configuration we have here. So why is this a better configuration? The biggest thing is that it helps lower the center of gravity of the van. So the original configuration had the center of gravity way above the floor, which it impacts not only the handling, but the way the drive feels. So this new configuration sinks that center of gravity. It also reduces the overall height of the battery packs to about 4 inches, meaning it doesn't really impede any of the space on the floor. And lastly, it opens up just more floor space. So even though it is about 4 inches thick there now, you still have the back of the van, and you can stack things on top of it. Makes things a little bit easier instead of having those 2 big boxes taking up some of that front space there. So where I started was disassembling the original battery packs. So the image there, I'm using the original aluminum extrusions just to kind of place and see what I can do with this floor. And I scavenged a lot of the original high voltage cables, some of the sheathing and wire loom, and the original inlet and outlet ports for the coolant. You can kind of see it in the bottom corner there. And I tried to maintain sort of as much as I could from the original project because my budget was quite low. So compared to the original budget that was in the tens of thousands, I only had about 1,700 to work with. And that's what I could get from the school. So given that kind of budget, I had to take some liberties where I could. But from that, I did make some improvements. So the original thermal system did use vinyl, and vinyl has a nasty habit of degrading when you put propylene glycol into it. So instead, I substituted out for EDPM rubber tubing. I also noticed that, and Austin pointed this out, they used screw clamps before, which with time can get loose and come off the connections there. So I replaced that with constant tension spring clamps to ensure that they stayed. And I put the original screw clamps back on for redundancy purposes. And then now in the new layout, the tubing runs through the center of the box versus in the original design, it kind of went up, snaked up, and then came back down, went back through the floor and came back up. So now it's all just one solid, just flowing system. Now, of course, I still need to test to see if the pressure will be maintained, to see how the flow will be, because of course there's some weird angles in there, but that will be for this semester. Now, updated design also includes some stuff for the high voltage. So on the terminal connections, I put insulative material. So this is a custom TPU cover that I've created. What I noticed, and this is by accident, when I was building the frame, I had dropped a piece of extrusion on one of the battery modules and it contacted both ends and kind of sparked everywhere. I was like, I don't want to deal with that. That is way too dangerous for me. So I created this TPU sheath. It goes over the actual, it's a nut that sits on the terminal. That way, if anything happens, it's going to have to go through that TPU first, which is about 1/8 of an inch thick. And it's pretty tough, I would say. And next, I've been playing with, this is a 3D printed mock-up, but this is the switch that will help bring the voltage down from 360 to 120 in the front, 240 in the back. So at least that way, it's less dangerous to deal with. Now, this isn't ideal. There's still a lot more work to be done if we want to actually install a true manual service disconnect, but this is a start. This makes sure that if someone wants to work on the system, it's already being discharged in some way. So that's an improvement from what I got, where you just take your wrench, you go on the bolt, and you go for it. And I'm open to any suggestions. I know you guys have experience with EVs, working on EVs. This is my first time doing this. So any sort of advice you may have for me, we'll get to that. So finishing touches in the future, of course, this semester, I'll be building the actual sheet metal battery box. So covering the whole thing up, making sure that it's safe and nothing can actually penetrate the modules. I will be installing on top of it what I call a false floor. So this would be some material, wood, maybe something else that will go on top of the actual battery box to ensure that, let's say someone drops a drill or drops a hammer, it doesn't just go straight into the sheet metal. There's something else that are protected from damage. And that way it's a disposable material. You can just replace it, put something new to ensure you protect your modules. And lastly, I keep mentioning it, we have to test the thermals because right now it's not very clear how well it will work to actually cool the batteries under heavy use, but hopefully we'll get a better idea by testing the coolant, the temperature of the motors, everything else there. So future plans and possibilities. and some things that I've been brainstorming. Of course, you have to redesign the drivetrain, make sure this thing doesn't shear itself apart on highway speeds. So, of course, it's very important for highway driving that your drivetrain is solid. And this will also open up more opportunities for uses for the van, because right now, during the summers, it's only really getting used to move materials from the north side of campus to the south side. That's all it's really doing. So by improving the drivetrain, improving the usability, there are parts of campus that are further out. So maybe we could even use it for deliveries to what's called the Ion District downtown, bring things to and from, or maybe even have our workers go pick up materials at the depots where they get them. Just ideas there. The next one that Dr. Trevas has suggested was implementing a vehicle to load system. So some sort of way that would enable devices to be plugged in. Let's think about lights, speakers, power tools, any sort of thing that would enable us to use this huge battery pack that we have in the van. And another advantage would be that, let's say a building loses power. We don't have to use diesel generators anymore. You just bring the van over, plug it in, you get power for however long you need. Now, the other thing I need to do is, of course, create a comprehensive maintenance schedule and repair guide, because not many people know how to work in EVs, and I'm sure that people here need to know. So, of course, giving detailed instructions for the battery disassembly. This is a unique design, to say the least. So having a way for people to know, okay, this is how you safely disconnect the high voltage lines. You need to disconnect your BMS. You need to make sure that this is taken care of. Step-by-step instructions to pass it on to whoever's next after me. And of course, just general maintenance advice and care for the electronics and mechanical systems. Since this does use some of the original mechanical systems from the P30, it's also important that people know how to work on a P30. And another thing to note is that this does use a lot of components from other vehicles. So there's components from Corvette, funnily enough, Hyundai, Ford. It's a hodgepodge of different things. So understanding how those systems interact and what they do for the vehicle is also very important. Of course, lastly, when all this is said and done, be able to give it to our client, Housing and Dining. So this is their vehicle. They did sponsor this project. They're the ones who provided all the funding for this project. So ensuring that it is ready for them to use whenever they need it is the most important part. So I'd like to just quickly acknowledge my project supervisor, Dr. Odin. She was the one who signed off on this whole thing, helped me get the funding, gave me the space and the time. My faculty mentors, Dr. Trevas, he's in the back there. Big shout out to him. He's been a great supporter. And also Dr. Schaefer, she helped me with some of the initial calculations. The OEDK faculty and staff, they provided a lot of additional advice, the tools, and just the know-how on how to do some of the stuff for me. And special thanks to Austin Greer. He's going to present after me, but he is the one, the mastermind behind this project. He gave me a lot of excellent expertise about EVs. He's been doing this for years. Really cool guy. You'll hear from him soon. Of course, 2 sponsors for this project. Housing and Dining gave me the majority of the money, about $1,200. ODK gave me about $500. So with all that being said and done, I'd like to open the floor to questions. Yes, Dr. Charles. Yes, right. So Omni, for original project, they had not only donated just the motor, they also gave a lot of donations periodically, and also their own engineers helped work on the project as well. So that's another big thing that they did. Omar, you have questions? So I did not know that. That's a very good point. Like I said, this is the first time I've ever worked on, like, this project for me was quite literally my introduction into the world of EVs. And that's why it was like so exciting for me. And that's something Austin sort of, he and I were close my freshman year. He sort of talked me into doing this whole thing. But yeah, that's a good thing you mentioned there. I'll definitely look into that, getting the proper sheathing for it.
I also have another question for the powertrain.
Yes.
Is there a reason why you just didn't put the motor directly onto like a 9-inch Ford axle and use torque algorithms to, instead of powering it through a prop shaft?
So that's a question more for Austin. So again, I inherited this project. The state that I found it in, it was not driving. People were afraid to touch it. The battery box was already pretty much disassembled. So I was like, okay, I'm just going to work on getting this thing driving again. So a lot of stuff that I'm learning now, I maybe give me a month or 2, I can answer your question. But Austin, he'll follow me. You can grill him on any sort of very specific details. Any other questions here? You sure, sir? That is something I haven't really heard much about. So But I think if we did have a program like that, it'd be very beneficial because EVs are becoming a bigger and better thing. And
Solar charging system.
right. So we do have the infrastructure, but we don't necessarily have the know-how. So this project is the first of many, hopefully, to come. But with time, we should be able to build a program like you're talking about. The back. Yes, sir.
Yes, sir. I was curious about the configuration. It is, yeah, it is. Yeah. You can hear me. Yeah, the configuration. Oh, the configuration of the battery pack. You mentioned it was 300 volts,
400 volts.
400 volts. Is it essentially a series connection of all the cells?
Right. So if I go back a few slides here, here. So with the flat configuration, it is a series connection. So the way it is wired right now, the front 6 go through a fuse that then goes into the rest, the rear modules. Those then connect in series, one by one, slowly ramping up your voltage. I think by each one's about 24 volts, so they bump it up by 24.
Oh, so each of those boxes is 24 volts?
I believe so. If the math checks out, there's something around 24 volts each.
Okay.
So each one, because it's in series, we'll just bump it up, bump it up,
Is it,
bump it up.
is it one of those scary things if you have to replace one of those modules? That is, you got V plus and V minus, and you got to disconnect a bolt and wrap it with a non-conducting tape.
So
While you
when
pucker
I
up.
first started working on the van, it was stuff like that because it was, again, there were many things that the students probably weren't aware of when designing this for the first time. But with time now, I'm making it so then you don't have to go in and worry about wrapping yourself with electrical tape. But at least for the front pack, because it's a lower voltage, I think it'll be sitting at 120 after you take off the switch. I would still wear some gloves, but you don't have to worry about, short circuiting all the electronics if your ratchet like hits the frame or anything like that.
We have a rule generally, we wrap our wrenches with non-conducting tape.
I've done that a few times
Yeah.
now, yeah.
And what is the amps at full acceleration, out of curiosity?
Oof. I believe it's about 1,000 amps, full draw, but the continuous amperage, I believe, was 600. I think Austin may touch on that since he worked a lot more with the electronics. But yeah, it's something around.
That seems high. I have an electric truck, and when you full acceleration, it's 300 amps, but
Okay.
it operates at lower voltage.
Right.
Austin, let's keep in mind what Brad's job was, is actually to fix the broken truck.
Right. So I'm just the repair guy. But these are very good questions.
I just have one simple question. What type of charge port did you use on it? NAX or J1772? Because I saw in the chat that he said it charges for 14 hours on L2.
Let's see what he said in the chat then. I'm not sure. Just be bluntly honest, I'm not sure.
The video, it looked like a 1772.
Yeah.
One further question, the vibration.
Yeah.
Is that an interaction between the motor? Was there an encoder on the motor, for example? An interaction between the motor and the mechanical elements transmitting torque?
Right. I think from what the team relayed to me was that there was some sort of weird interaction between the motor itself, the way it was producing the revolutions from the axle, and how that transferred into the rest of the system. But also, I mean, the fact that the intermediate shaft, so the solid axle I showed, there's nothing supporting it. It's just floating in air, and then the rear axle is the one that's also spinning. So with that being said, already any sort of vibration in the system will just be amplified because there's nothing keeping it in place. There's no center support as of right now.
Fred, are you working on this on your own? Just you?
Yes. So Austin, again, he was the mastermind. He gave me very good personalized advice. Unfortunately, he is in law school right now, so I can only really get asynchronous advice. But for the majority of the project, it was just me working on it in the class time that was allotted. And then I would have friends who would kind of help with the grunt work, like lifting these batteries. I mean, it's 300 pounds of batteries we had to move in and out of the ODEC, or cutting the extrusion, whatever it was. But it was me doing most of it.
And is this like a senior project for you?
It's not a senior design
No,
project.
okay.
This was an engineering design
Just-
studio. It's a 300 level course that I took.
Okay.
So it's an independent study, one that I did here through the ODK.
And so you're a junior this year,
Yes,
so
sir.
you got a semester and then the summer and then your senior year. What are you estimating your timeline for getting it ready to go?
I know that
Meeting
I
your
can-
goals.
I know I can get it driving and with a battery box by the end of this semester, so by May.
Okay.
Now, in terms of the drivetrain issues, the thermal, everything else, that's something I'll have to pass on either to a senior design team or to someone else like me who's interested in working on the project. And that's sort of the difficult part because this project can get very expensive very quickly and there are limited funds. So we'll see. But all I know is that by the end of this May, this thing will be up and driving again. It will be usable, may not be the best, but we at least know, okay, this is something that needs to be fixed. This is another thing that can be worked on. So that at least that way it can be a continuation if need be. I also don't know that. I believe there was an answer also in the chat. Okay, 6,500 pounds was the answer there.
So quick question.
Yes.
What do you think is the most important thing you learned out of all of this?
Ooh. Most important thing.
Or things.
There are definitely a couple of things. So whoever said safety first, that's the biggest one for me. There were a few times where it's like, okay, I got to definitely read up on how to take care of this. But I think just EVs in general, because I had never really looked into EVs before this. I kind of passed them off as a joke, like, it's just a toy. What are you going to do? But then working on this project, seeing the technology that goes into it and experiencing the design process as I went on, I was like, wow, this is really neat stuff. I mean, this has the potential to be something great. So that for me was the magic moment. And especially since Austin and I, we had worked together in the past. I mean, he introduced me to EVAN. I got to drive it a couple of times. I mean, that sort of interaction is what kind of got me here. But definitely being able to work on this project from the ground up, getting it from their bare bones. So nothing in the van, like I took the batteries out, had to check them. I went through most of the cells by hand, checking them all this, like it was deep in the trenches, but that was something that excited me and kind of taught me a lot about the fundamentals of engineering, I would say, especially for electric vehicles.
Sure, you put that in your resume.
100%. All right. I think technically, yes. The first EV I've ever worked on, first EV I've ever driven. So with that, thank you very much for your questions. Austin will be presenting next. You can grill him even more, but thank you very much.
Okay, everybody hear me?
Nope. Yeah, go ahead, Austin.
Okay, let me see if I can get set up here. Presenting. Okay, can everybody, well, y'all can't, there we go. Okay. Welcome everybody. Thank you for taking an interest in our project and coming down to Rice to check it out. I'm Austin Greer. I was fortunate enough to be part of the project when it began several years ago. If you have questions for me now, I'm happy to take them. And then we can also do questions at the end. I tried to answer as many as were being thrown out in the chat, but I can take a few now if anybody has any. I hear noise, but
So Austin, why did you choose to channel the power through a prop shaft instead of putting the electric motor right on the axle and using a sturdier axle like a 4 9-inch with a planetary gear system and using torque algorithms to control the output so it doesn't explode the axle?
mainly cost and time.
Okay.
And we also are working with Omni Powertrain, which they do have an e-axle setup, but it's set up for independent suspension. And so in order to be able to use one of their powertrains, which we really wanted to do, if we went with an axle-based setup, we would have to do independent suspension in the back to be able to, kind of like the F-150 Lightning. And with the time and scope, I was really concerned about pulling that off. There were talks about doing that and actually doing it in the front too. So a all-wheel drive setup with independent suspension all the way around, but just cost and time. That would totally be the way to go with unlimited cost and time for sure.
Thank you.
Of course. Okay, well, before we get into a little bit about the van, here's a little bit about myself. So this here is the humble beginnings of my battery electric explorations. These are my, at least one of my dueling Chevy S10s. I had two of them. This one here is the Chevy S10 Blazer, but these two trucks were my learning platform for really figuring out what is an electric vehicle, kind of like this van is for Brad. The high voltage architecture, kind of just real basic stuff. This one had a hood mounted motor controller for cooling. That was done like halfway through the project because it wasn't cooling enough where I had it. So just gave it a functional hood scoop. I think it's the only EV out there with a functional hood scoop. But it was very, very rudimentary. Although I was very proud of my 47 miles of electric range that I took a picture of there on the old Garmin GPS back in probably 2016. This thing had lead acid batteries in it. So for a 4,000-pound brick with lead acid batteries in it, 47 miles of range, I don't think is too bad at all. But no lithium yet. That comes later. Batteries are too expensive back then. I made a jump because batteries were too expensive. So we have to make a pit stop on my automotive journey. And so I moved back into the gasoline world with my 1984 Lincoln Town Car and the 302 cubic inch high output V8. This is my grandmother's car. It's been in the family since '85. It's been in a barn since '95, and I pulled it out shortly after I kind of wrapped up the S10s and started tinkering on this thing. So with this car, I started to hone a lot of my skills, specifically general electrical skills. If you could see inside the S10, if you think the van is bad, I'll explain a little bit about why it was so bad, the battery boxes. But if you could see inside the S10, you would think the van is really good because the van was wired with like literal Home Depot parts and extension cords because that's what I could get. That's what I had available. And so with the town car, I really started to improve what it means to develop kind of an electrical wiring system with a car. So I installed this gigantic piece of plywood in the trunk. It's kind of slid out on a tray from where the spare tire used to go. And while it still looks messy, it was a lot better than before on other projects. And it really allowed me to get into understanding programming, electronics. There's some Arduinos on that piece of wood. Wiring system durability, why you can't use things like wire nuts and Home Depot parts in cars, what wire abrasion is, how to prevent it. And it allowed me to do some cool stuff like that, like the digital dash right there. So I started getting to kind of some technology features as well. Fast forward a little bit, and I came back to the BEV world when lithium batteries got cheap. So this is the electric HHR that I built. Took a Chevy HHR and did exactly, well, not exactly what I did with the van, but from a powertrain perspective, something pretty similar. Tesla Model S batteries. It had a 100-mile range. This was my version of a Nissan Leaf, basically. I wanted to really level up from the S10s to something that's daily drivable and reliable. And this was. I drove this to school in college at Rice for most of my time there. It had air conditioning, heating, power steering, power brakes, nothing fancy. No, it had a pseudo digital dash, but it was mainly just for your like battery information and range and all that stuff. I kept the factory dash in it. So a pretty basic conversion, but just really simple, very reliable. The HHR is a very small vehicle, so the batteries were still sort of in the passenger cabin. I removed the false floor that I had in that picture in the top left corner of the screen so you could actually see the cells. So there was a bit of space intrusion, but overall it was still a pretty practical, usable little car. And it gave me great confidence in that, hey, I can do an EV conversion, and it doesn't, it will actually work. And then I jumped back to Team Blue Oval on the town car. I took it back apart, as you can see, from the disassembled town car that you're looking at. Pulled it, all the interior parts out. Didn't do an engine out this time, but there were just a lot of quality of life upgrades, like a new dashboard that you can see there in the bottom right corner. But also, critically for the van project, this iteration of the town car had what I started to call the multi-purpose vehicle control unit, or MVCU. You can see that in the top right corner. It's kind of a little magic black box, if you will. And at this point, these were just glorified Arduino shields, but just kind of designed for automotive control. However, they were CAN bus enabled. So each of these multi-purpose control modules that were mostly the same, a little bit different depending on what exactly they were controlling, but they were CAN bus enabled, and they could all talk to each other and control various vehicle functions without having to have all those wires you saw previously in the trunk. So no more chunk of wood in the trunk. And if you're familiar with modern cars, this is starting to look more and more like a modern car's electrical system. Although if you're wondering why an 84 town car needs this, the answer is probably it doesn't. This is more experimental so that I can do things like the van. So speaking of the van, back to Team Bowtie. Interestingly, every EV conversion I've done, I think, has been on a Chevy. The S10s, the HHR, and now the P30. All the Fords are gas powered so far. One was almost plug-in hybrid, but not quite. So you've heard from the project about Brad and kind of all the technical details. I can answer questions about that, but I'm just going to try to give a highlight of what it was like to be on the inside at the beginning of the project, through the project, and kind of at the end of the project. So Rice's sustainability department reached out to various professors to see if anybody would be interested in doing an EV conversion on an old delivery van as part of a class, like build a class around the entire project. And there's not a lot of automotive stuff at Rice, at least there wasn't at the time. And so there was no professors that were interested in taking up this EV project challenge that the sustainability department issued. I see in the chat, nice acronym. We'll get there. So because nobody took the sustainability department up on this project, but Dr. Trevas heard about it, he came to me knowing about the HHR and the town car and said, hey, Austin, Rice wants this project done. They want an EV conversion on this old Chevy van. And are you interested? And I said, well, if it can be senior design for me, I'm interested. He said, yes, thankfully. And so there we go. We got the start on the project. And so I got this van that was truly cheap, hardly effective, virtually running on luck every time. As a matter of fact, I got it running poorly, but it ran. And the engine actually locked up as I was coasting into the parking lot, where I ultimately pulled the engine out of it. It was really on its last leg. However, could have been worse, because this van is the van that I was initially told we would be converting, or I would be converting if I was interested. This is a 1968 Chevy P20. It had the straight six 292 in it, which was permanently locked up from years of water dripping down the intake. Frame was pretty rusted. It was as tired as it looks. So after looking at this van here, I thought it was going to take about $100,000 to bring it back to life and do the conversion. And so this is what this is the van that all of my economic calculations were based on. Fortunately, Rice said, hey, that's a little much money. We've got this 97. What about the 97? And so that sounds a whole lot better. And the 97 is a 1 ton. This is a 3/4 ton. So it's a little bit heavier duty, which was nice too. So what was the goal? I think Brad had a goal that was nice and wordy, but my goal was, like this little sticker says underneath the hood of the P30, build simply the best electric vehicle conversion that we could possibly pull off. Uncompromising as possible, as reliable, and with as many features as we could have with reasonable simplicity. And so that is what I set out to do, and that is what the teams joined me on, the senior design teams joined me on shortly after. And so I dove right in, quite literally. This is the first day I worked on the van, the first couple days. I think it took us a couple days to get this out. This is before senior design. This is in the spring of 2023. And it was just me and a friend. And we got the 4.3 Vortec and the 4L80 pulled out of it. The engine actually comes out the door on these step vans, so that was a bit interesting to do there. But got the project off to the races. And here's some just kind of pictures somewhere along the way. The two on the top are kind of just interior pic shots along the way. I'll talk about those. And then down below in the left corner is the first test drive, and on the right is just kind of prior to delivery, final delivery to housing and dining. But ultimately, through all the stuff that Brad talked about, all the batteries and specs and the issues and challenges we had, we were able to include so many quality and convenience features that took this thing from the technology level of the 1950s. This thing had the same equipment that my 55 F100 has, to a modern, safe vehicle. We have electric power steering on the column. You can see in the top right the column and the power steering assist motor from a Mazda CX-9. We were able to directly interface with the steering column control module that's built into that steering column. So we only had like 5 wires going to the steering column to do everything on the steering column: the electric assist, all the buttons, and the turn signal stalks and wiper stalks. Really optimized as far as a wiring harness perspective goes. We were able to incorporate shift-by-wire parts from a Honda Odyssey and a Chevy Corvette. I think Brad mentioned the Chevy Corvette parts. That's where that came in. Android Auto, Apple CarPlay, heating and air conditioning parts from a Honda CR-V, blind spot monitoring from a Mazda 3, battery system, like Brad said, Tesla batteries, Orion BMS, motors and inverters, and gearbox, courtesy of Omni Power, heated and cooled seats from a Nissan Altima, Maxima actually, dashboard using a Samsung tablet, cooling parts from Tesla, and all these different parts from all these different manufacturers that were never designed to go together. From an electrical architecture perspective, we were able to make function, using what I had learned and what I had developed previously, and then iterating a little bit on that. Those multi-purpose vehicle control units, MVCUs, we have 5 of those throughout the van, and they were able to interface with all these different parts, give them the data that they needed from all the other components in the van so that they could function while still making the component itself happy and thinking it's in its original vehicle. Or in the case of like the tablet for the dashboard, talking to it over Bluetooth. All those features are packed into the multi-purpose vehicle control or multi-purpose control unit. Everything from the factory dome light in this thing to the electric drivetrain works seamlessly because of all the work that was put in to the electrical system by all the teams and some of the research I had done previously with the R&D on some of the previous projects. But the electrical architecture is what makes this thing function. It is a seamless vehicle. You saw in the little video that Brad played, there's multiple ways to start it. One is with a key fob, one is with the RFID card, which was what was shown in the video. But just being able to get in, put your foot on the brake, tap your card and hit the start button, and everything light up and function with no DTCs in it. That is what I was striving for in this project, and that is what all the teams were working towards, and we got there. Now, from a practical standpoint, we did not have the time or the manufacturing capability to do everything we wanted to do. Brad is being kind to us, but this truck vibrates all over the place. I mean, the drive shaft, the drive line is not what it was intended to be. It's not the drive line that was intended to be in the truck. For time and cost reasons, we actually had to scavenge from that 1968 P20 in order to get the thing working. And we wanted to make sure that the range was as good as it could be, and at least use the money that we had while we had it to buy the parts we were allowed to buy and get that big battery pack, get it purchased, and get it in the truck somehow, so that at least later on somebody like Brad could come and make a better battery box. The team that was on battery box just did not have the time to do the battery boxes, all of the cooling, work with a thermal team to get the cooling working, and all have it be perfect. However, it was still a solid vehicle. We drove it over 1,000 miles. I drove it all over the place. Campus, bumps, burnouts, donuts, hard brakes, swerve, highway speed, max speed, everything. What happened to the battery packs, to color it in a little bit more about the failure Brad was talking about, I provided a service manual, kind of an engineering service manual, like not step by step, here's how to do everything, but here's everything that's in the van. Here's all the information that we used to build it. That was passed on to another team. Unfortunately, when they were doing some maintenance on a simple coolant leak, somehow some improper repair procedures got carried out, and we had that battery container failure that Brad talked about last year. And that's because serviceability was atrocious. That was on the table for me in terms of an electrical architecture perspective. And big picture, it was on the table, but when rubber met the road, we were trying to get things done, and unfortunately serviceability really did take a back seat, which I'm not happy about. Unfortunately, Brad is helping us fix that problem. So very thankful to Brad and Dr. Trevas for all their efforts to get this thing truly perfect as we intended it to be, because it is so close. All of the like stuff and sourcing and the money, most of it has been taken care of. We just need a little bit more. And so we're doing an excellent job putting this thing. I'm very pleased with the progress that has been made on it this semester. It went from not running at the beginning of the semester to running. That's more than I think you could ever ask for. And so we'll come back to the van, but in terms of like me and some of the stuff that was learned on the project and all of the knowledge that was created through the project, what is next? We've heard about the capabilities of the multipurpose vehicle control unit. And I kind of realized the importance of that, because the van would not have been possible without an architecture like that to connect parts from all over the place together and make them work seamlessly like a modern car. And so I've started to kind of explore that a little bit further with a couple different vehicles. One is a 1954 Ford F100. It's getting a frame swap onto a 2010 Ford Explorer chassis. The other is actually that Honda Clarity that's in the background, which has nothing to do with the frame swap. It just happens to be in the background. And of course, with the Lincoln, it's kind of always the perpetual test bed vehicle. But in particular, I hope to have a custom dashboard that's not based on a Samsung tablet, but it's actually like custom made for automotive use, like the one you see in the top left corner that I'm got prototype testing right now on the Lincoln. And I hope to have that available soon for sale. I know there's not much of a market for digital dashboards for 84 town cars, but you can see kind of the capability that I have based on that picture to kind of design a retro dashboard. And I think that would be great for lots of vehicles. I personally have a 55 F100, and to buy a dash for that, that's a factory OEM style dash, is like $1,200. This one you can get for $200 or $300, and you can put anything on it. Navigation, use it as your head unit for music, use it as a touchscreen to control different functions in the vehicle. Super, super flexible, super cheap, and so far has been super reliable. The version, both in the van, the Samsung tablet's reliable enough, but this is kind of purpose-built and is a drop-in replacement. And so I've been working on mechanical design and manufacturing techniques to kind of figure out how to leverage the architecture there in that picture into custom drop-in replacements for various classic cars. I also have several customized multi-purpose vehicle control units that I hope to have available for sale. One in particular is an electric hydraulic power steering controller. That's different than what we had on the van. The Lincoln actually has an electric hydraulic power steering pump now. And so from that project, having a standalone controller that anyone can buy and put electric power steering in a car that has a hydraulic power steering rack, if you don't have the room for electric power steering on the column like we had in the van. Also a customized multi-purpose vehicle control unit for Ford 30-way power seats. I know that's kind of a random thing, but you saw in the van that we put a heated and cooled seat in that. And I wanted to, I think driver comfort is very important. And so I wanted to take that up to the next level. And I was like, what's the best, cheapest seat I can get? And I was told Ford 30-way multi-contour seats. And I got some, and they're very comfortable. And then I made a custom controller that controls everything on those seats. All the 30 ways, all the lumbars, all the heated and cooled and stuff like that. So I hope to have a controller like that for sale. So if anybody wants to put that in a project vehicle, they can also do that. And then maybe on down the line, bring in some stuff, kind of resurrecting it from the van project, things like a standalone blind spot controller, standalone electric power steering on the column controller, like a Honda shift-by-wire controller, GM parking brake controller, some of these things that could be very useful for all kinds of custom vehicle projects. And I certainly have used even since the van, maybe bringing those to market in terms of controllers for those OEM parts so that other people can kind of do have some of the same similar features that we had on the van in their own projects. I'm toying with the idea of turning that into developing full wiring harnesses for certain classic vehicles. There's a lot of difficulty that goes into that. I worked for Honda Development Manufacturing North America on integrated controls team focused on wiring harnesses. So I know what it's like to build a wiring harness for an OEM production vehicle. And so manufacturing that on scale is a challenge all its own. But hopefully the Ford Explorer frame swap project is going to help me explore that, because that's going to get a full custom wiring harness. So that is kind of where the technology that came out of the van is going. Brad's talking about where the van is literally going, and I'm talking kind of where some of the research is going that kind of went into the van. The pictures on the right are the 54 F100 body. In the top, the old engine's getting pulled out. It had a 393 stroker motor in it, I think. I'm not too sure on what engine that was, but it needed to be yanked out for various reasons. This is not my truck, by the way. I'm doing this for a customer. However, the bottom picture there is the truck on the Explorer chassis, and the internet said it wouldn't fit. So yeah, it fits. Anyways, thank you for visiting Evan and Rice University. Glad to have everybody there. Sorry I can't be there in person. I'm in the Fort Worth area for law school, as Brad said. But if you're interested in some more of my automotive exploits, there's a whole lot more. And some other various random things like solar panels and me tinkering and fixing stuff. I have a small YouTube channel there if you'd like to check it out. And big thanks to Omni Powertrain at the bottom. They do commercial electric motors and pumps and hydraulics and gear assemblies for all kinds of commercial applications. They make motors for the Ryobi zero-turn electric mowers, all the way up to oil and gas stuff and cranes and lifts and things like that. So definitely check them out if you have a company that could benefit from their services. All right. Any questions? I've probably got at least some out there.
All right.
So I loved your acronym. In the halls of the glass house at Dearborn, we call that constantly having every vehicle recalled over lousy engineering techniques.
Yeah.
Second,
yes.
I see your progression on networks, on vehicle networks. You're moving from hardwire to CAN bus systems. On your next iteration, are you going to explore zonal networking?
I have looked into that. I know that is starting to come down the pipeline. And I think it's not the Explorer frame swap project may be challenging to do that on, but it's coming. It's coming. So
also on your commercial wiring harnesses, do not use soy. Rats and squirrels eat them in the Midwest.
Yes, Honda discovered that. Honda has a special tape that they sell as a Honda part for anti-rodent protection, a little like electrical tape, but it has like a rat with like a big like cross over the rat, like rat killing tape. So yes.
Okay, so over here we have John with a question.
Yeah, I had questions about the motor, but you have a lot going on for someone who's also in law school, I believe, right?
Yeah, that is true. That is true. I'm in law school.
So yeah, the motor on the van, I think you also said that they gave you a gearbox, and so that was really great.
Yes.
So what is the reduction and what's the max RPM? And I believe the drive shaft is pretty long, which is part of the problem, right? It's probably like 6 feet long or something. Can you tell us a little bit about that?
It really needs a two-piece drive shaft at the very least, I believe. Gear reduction's like 8.5 to 1. The rear gear set in the van's a 456 to 1. And I think motor redlines it somewhere in between 8 and 10,000 RPM, something like that. So it gets spinning pretty quick. Top speed on the van is about 80 miles an hour, just a hair over 80 miles an hour. So
okay,
I got a
question.
Yeah, so got a question about it looks like he was a little worried about maybe having the voltage too high. Do you have, or does the controller that that comes with the motor, does it provide a pre-charge circuit or pre-charge resistor, or are you guys using a contactor? Because you mentioned a manual switch, but are you guys also using like a relay that disconnects main pack voltage?
It does. It's got the exact same. It has the system out of a Tesla Model S. So the disconnect in a Model S battery pack, at least the P100D that we got, is the fuse. You unbolt the high voltage fuse, and that is your disconnect. That was our disconnect. It's just hard to get to, and so like Brad said, you're fiddling with those bolts trying to get it out, and then that's connected to the Tesla Model S. I think Gigavac is the contactor manufacturer, but connected to the two contactors that the Model S used. So yes, and then there's a pre-charge system is controlled. We hacked into the original Tesla circuit board for pre-charging, and one of our MVCUs controls the pre-charge.
Hey, Austin, I just want to thank you for making the time to come do this. This is really fantastic. And I want to tell everybody here, by the way, that Lincoln that he did, he submitted it to the engineering design showcase as an individual. And you'll see these posters are all done by teams. And so he just came and showed off that. And he won a major prize that was normally given to a whole team. So he's a remarkable young man. Really, he's just terrific. And I want to say thank you so much for doing this. But I want to jump in before, I'm sure other people have more questions for you, but thanks and good luck in law school. But we miss you here in engineering.
Thank you. And thank you for your help making the van possible and for making the version of Lincoln that we took to the design showcase possible, because I could not have done that without your help and sponsorship. I will probably ultimately wind up back in the engineering world in some way. It's still in my heart, so don't worry.
Yeah, that's a place I think you fit in. So besides folks in the room asking questions, do you have access to the chat, Austin? Are there some questions in there that you'd like to?
I do. I have. I'll bring them up on my laptop here. Let's see. Accuracy of the range. Guessometer for the truck. It's pretty accurate. The Orion BMS does a good job of calculating. It's got a bunch of temperature sensors on it, cell taps for every group of cells. And so it's a pretty good estimate. I've never had it let me down in terms of telling me it was more charged than it was. It was always it seemed to be accurate enough to keep me safe. Max cargo weight. I say it's 1 ton because that's what it's supposed to be for a 1 ton truck. We did upgrade the springs. We added 1,000 pounds to it. And so we've upgraded the springs. So it can take more than a ton before it hits before it even hits its original gross vehicle weight rating, much less what the springs are rated to carry. Drop in range when fully loaded? No clue, because we never fully loaded it. I would venture to say not much, because the efficiency is extraordinarily low because it's so unaerodynamic. And so unless you were towing something, which I don't think it even has a tow bar on it, but I would say it probably doesn't drop very much because weight generally isn't as big of a factor as aerodynamics, and aerodynamics is a huge factor in the range of this truck. It's probably going to impact it more in city driving. But of course you have regenerative braking for city driving. So as you're accelerating things up, you can get a little bit of it back anyways, slowing down. So we never fully loaded the thing. We had it pretty loaded, mostly with people. We took a lot of people around. It's probably the heaviest thing we had in it. We had it full of like 15 people at one time, packed in there like sardines, and it used a tiny bit more. So I think those are all the questions in the chat.
Okay, that takes care of the chat questions. Over here, John.
I have another question again. Austin, it's very impressive. I really loved the work that you've done on the digital dash stuff. I'm working on my second conversion, which is a mid-size pickup truck with some Tesla motors in it and a Didion axle for the rear. And I would definitely like to connect with you about the dash kind of stuff, because that's on my list of things I would love to do. So let us know the best way to connect with you on some of those projects.
Sure. Would love the connection here. I'll drop my email in the chat. Do you have access to the chat? You may not if you're there in person, but hopefully somebody can forward that. Austin Greer 06 at Gmail. That's just my name, Austin Greer, Greer 06 at Gmail, and it's in the chat too. So yeah, I would definitely love to kind of get it out there, and I have some of my parts running around in other people's vehicles, one of them being the van, and I have a few other kind of prototype testing things out there. So definitely would love to help out with getting your dashboard and electronics needs taken care of. Question in the chat. I've seen some companies adding solar panels to buses, trucks, and other vehicles with large surface areas. Is it possible with this truck? Well, it's possible. You can strap solar panels to anything. But I mean, it's not super helpful. Somebody was curious, and so they did the calculations and came up with something stupid, like it would take like 3 months to fully charge it on an average day in Houston, parked in a parking lot with the number of solar panels so you could fit on the roof, accounting for kind of some cloudy days and things. So I was like, yeah, maybe not so much. I think we determined like a couple miles of range a week just because it's so thirsty on power and there's so little space really on the top of the thing. So
Austin, I have one more question. Did you do any efficiency calculations on what the kilowatt per mile is of the vehicle?
1. Yeah, yeah, it's rough. 1 kilowatt hour for 1 mile, 1 to 1. It's pretty. It's like maybe 1.1, but it's pretty close to 1, is what the calculations said, and that's what it turned out to be in real life. The calculations didn't lie. So
Don't worry, that's really good. That's what the lightning gets towing. So
yeah, yep.
More questions in the room? All right, and if you stay online here, Austin, then after Sebastian, in case people think of some more questions for you, then maybe we have an opportunity that you could answer those too, or if you have to run, I understand, but
I'll be here.
Good.
Can answer questions
Perfect.
anytime. I'll try to keep an eye on the chat too. Thank y'all. Enjoyed talking. Thank y'all for coming and listening to our project. It really warms my heart that people are interested in it this many years after I started. So
okay, so we have Sebastian coming up here now.
Austin, can you release your share?
Okay.
Because I also have.
Okay, so while they're getting started there, I can tell everybody's having a lot of fun, which is good. Yeah, John.
So I don't know if y'all remember Ken Masterson, the EV boat guy. A few of us went down to see his boat like a few years ago. Anyway, on Facebook, he's selling that boat. So I saw it like a week ago or so. And it has, it's a pretty big boat. It has a bunch of Tesla battery modules in it. And what else? I'm trying to remember the drivetrain. It's I think it's a 3-phase drivetrain, I think with 2 motors, something like that. Anyway, I just thought it would be interesting. If anyone's interested in an EV boat, you should look up Ken Masterson on Facebook. Just search EV boats.
Does he still have it on Lake Conroe? I remember that's where we saw it.
You see his big boat. He took us
Oh.
around the aluminum boat.
Oh, so this is a bigger boat.
Fiberglass boat?
Yeah, I saw that.
Oh, you did see it?
Yeah.
But we didn't have it out on the water, there, did we?
No, I think he had it on a trailer.
Okay.
Right, yeah.
Okay. So he's done multiple boats. All right. They're getting bigger, just like the electric airplanes are getting bigger. Good. So yeah, people can hunt that up. Okay. So you guys set up? All right. Yeah, you might want to grab it out of the stand. All right.
Hello, everyone. Testing. All right. Hi, everyone. Thank you so much for being here and having us present about our projects here. My name is, or I'll do a quick overview of the Rice Electric Vehicle team. I'll kind of cover a bunch of different things, but I definitely have time. If you want more specifics on anything, feel free to interrupt me and just ask. And we have a couple different presentations for each of our sub teams, so I can definitely find you more detail somewhere afterwards as well. Okay, perfect. All right, fair warning, I may ramble a little bit then. Sounds good. All right, so a little bit about me. I'm also a junior mechanical engineer from Rice. I am the chief engineer and solar car team founder at Rice Electric Vehicle. I've formerly competed in the high school solar car challenge, which is kind of where I became really passionate for this kind of stuff. Um, I'm pretty much like the only one in my family that's into engineering, so getting to have an outlet to go build things and make a meaningful impact with it at the same time is pretty cool. And I'm a big automotive and motorsports enthusiast as well. You can see me in my car in the top right, and then that car on the right side is my high school car. It was an aluminum monocoque solar car, and it did about as well as that carbon fiber car that's right next to it. So really proud of that. So first kind of bullet point about our team. We're a pretty interdisciplinary team made up of lots of different people. Just the nature of Rice so far, we're mostly engineers on our mechanical and electrical teams with a couple other majors as well. There's definitely a huge business side to it as well, with all the logistics, running a race team, and getting a lot of money and parts donated. We're hoping this semester to grow a media and marketing team. That way we can have an Instagram profile, network with sponsors and other people that are interested in it, as well as an operations team to kind of come up with team strategy and have an outlet for the people that might be interested, but not in technical or engineering ways. So we're a student club here at Rice University, one of several engineering clubs. So there's also a rocketry team, a wind energy team, and things like that. We're competing in the American Solar Challenge, which is a student-built EV endurance race with about 45 to 50 teams this year. We're actually a revival of a former team also called Rice Electric Vehicle Club that once competed in a different competition called the Shell Eco Marathon, which you might have heard of. We're building an all-new car and competing for the first time this summer in 2026. And there's a couple photos of, that's our mechanical team on the top. And of course we have in electrical engineering on the bottom. Shout out to our faculty advisor, Dr. Gary Woods. We are mostly engineers, as I mentioned before. There you can see kind of what the split is like, heavy mech and elec involvement. There's 15 of us that have leadership positions, but the thing that separates us from our peer institutions is that we're open to all students. So you don't have to be completely super involved, but we want everyone to have the opportunity to learn from it, to come to our general body meetings and hear about the industry, hear about innovations in EVs and things like that. So our largest of those general body meetings had around 45 people in attendance. And of course, all majors are welcome. So this is kind of our timeline so far. The past team had a small Shell Eco Marathon car. That chassis was built in 2015, so it was needing an upgrade. Funding was hard and the team wasn't able to make it happen. So knowing that if we wanted the club to come back, we'd need a whole new car. That's really what opened the opportunity to a solar car. And you can see there our preliminary mechanical design for that. I'll get more into that in a second. And in 2026, we're hoping to have our unveiling of a finished car. So solar cars, the American Solar Challenge is built of actually two separate competitions. The Formula Sun Grand Prix is a track race for the North American teams on real race circuits like Circuit of the Americas in Austin and most recently NCM Motorsports Park, which is the Corvette test track in Kentucky. And it's an endurance race, meaning they give you 3 days of racing. The team with the most mileage wins. And if you do well enough in that track race, you qualify for the Cross Country American Solar Challenge, which is a race from one city to another on roads. They definitely try and avoid things like Houston 80-mile-per-hour highways, but they are still on real roads. And then first team to the end wins. So it's if you've heard of like Cannonball Run or things like that, it's a lot like that, but with cars you've built yourself, which is a lot of fun to do. And then the most valuable part for us as students is called scrutineering. So that's essentially before they let you take your car on a real racetrack or on real roads, you have to prove that it's safe and explain your design, manufacturing process, and business choices to the competition judges. You have to pass a bunch of different inspections, submit a bunch of different reports, which we're doing right now. And it allows students to take ownership of essentially their subsystem of the car, their little piece of the car that they've worked on, and get to learn a lot of real life project management skills, like working with people in different disciplines, and also getting to apply the things they learn in class to real EVs that they're interested in. And so you can see some pictures from The top one is actually the international challenge. It's in Australia. We essentially take apart our cars, we show them to a bunch of judges, and they kind of grill us to make sure we actually understand the thing we've built and that we're qualified to take it out on the road or on the track. So what makes this competition unique is definitely, as I mentioned, that we're racing on real roads and real circuits, just like real cars would. That necessitates a whole bunch of like compliance requirements, legal requirements. Our car isn't going to be road legal this year. We're just targeting the track race. But lots of teams do end up having to go through the whole insurance and getting their car registered in their state process, which is pretty complex. In Texas, that incentivizes a lot of three-wheeled car designs for sure. But yeah, so it's also very interdisciplinary. That's another reason we chose it. Just that you don't have to be into cars specifically. You could be into things like energy, sustainability, business. And the competition is very accessible and supportive of new teams. We were able to get this far as a first-year team because a team in Montreal that actually won the competition in 2024 has essentially been mentoring us and provided a lot of the parts and designs we used for our car. So you can see a picture of their car there. Hopefully ours will look a lot like that when it is finished, and we'll be able to get some cool scenic shots when we take it up to the race. Yes.
The distance on that last photo, is that the race? So you travel 2,800 kilometers and whoever finishes at the end is the winner of that competition?
So this was, yes, this was the 2024 race though. The 2026 race will be a different set of cities. They actually haven't announced it yet. Rumor has it there's a certain historic road in the US that is 100 years old this year that they may be targeting, but just a rumor. Route 66, by the way.
About how far do you guys get on, or like maybe a winning team, do they get at the motor park, like over the course of those 3 days?
So typically around 800 miles is what we would do in high school. That was different though, because the high school races are speedways, like NASCAR speedways. That way you don't have to worry about turns and racing incidents with 16-year-olds driving. But the college ones would probably be around there because essentially the more lenient rules of high school kind of cancel out with college students actually knowing how to build cars. So they end up going around the same distances actually. So yeah, let me talk about just briefly our car. I'll get back to it in a second. It's solar powered. It has a carbon fiber chassis. Top speed of 70 miles per hour with 1 gear ratio is what our data indicates will be possible. And then the competition regulations now allow a 5 kilowatt hour battery, which, as you guys probably know, is pretty small. Essentially, as technology has been getting better, they try and nerf the cars a little bit to make sure we're not fighting the speed limit and getting speeding tickets on that cross country race. So we've done a lot of optimization with that. And as the batteries get smaller, it actually becomes more and more solar powered. I think one of the questions for Austin was something like, why don't you put solar arrays on the EVAN? So for us, that's actually a big aspect is we're getting closer and closer to where you actually can drive a car purely solar powered. Our solar array is around 4 meters squared of solar array at around 22% efficiency. You're making around 1,000 watts. So that means you have 1,000 watts of power you can send to your motor and drive forever, which can sustain a speed of, probably 40 something miles per hour in this kind of car. However, our car weighs 400 pounds and the EVAN probably weighs more than 10 times that. So technology is improving a lot, but still has a ways to go before we get to the place where an EVAN can be driven by solar power alone. And then here's some couple different views of our car. It doesn't have that bubble on the left side anymore, and it's probably not red anymore. We're actually still deciding what we want the livery to be. We're thinking a kind of light blue and red to match like the Houston Oilers type colors or something like that. Our problem with Rice is navy blue is a little bit pretty common of a color, so we're trying to differentiate it a little bit. But anyways, it's 4 meters long, putting it roughly the same size as a little bit smaller than the Porsche Boxster it'll be parked next to in length. But its wheelbase is a little bit shorter than that, since you can see that's just the solar array that's the big part. Our car is small compared to our competitors, which is good because we have a limited space to work with here at Rice. Essentially, I came in as a freshman into college wanting to do this project, and it took us until now. So this was designed for a rule set with smaller cars. So in the future, we'll probably be making a bigger car that are roughly the size of like a Honda Civic hatchback, something like that, a little bit shorter than a sedan would be, but very skinny. Ours has 4 wheels and is a traditional car layout, even though it's smaller. So it made a lot of the engineering work easier. And you can see the general layout is we have, it's called a catamaran design because you have the 2 different pods connected by that solar array. The driver sits in the left side and all the high voltage electronics sit in the right side. And then just one. So it could be 2, but the motor is the most expensive part of the car at around $25,000. So we're doing 1 this year. So we would do the right rear wheel. Our chassis can accommodate either, actually. Depending on the track is actually how we'll make that decision. Putting it on the right side is the easiest because that's where the battery pack is, and then all your high voltage is just in one half of the car. As long as you don't hit the accelerator too hard, it's not that big of an issue to just have one-wheel drive. But you just can't floor it. Your low resistance tires will spin pretty easily. DC motor. I'll get to the motor in a sec. I actually have a slide just about it. And this is kind of where it is right now. Just carbon fiber shell, painted white. And we have some suspension parts machined for it that have been inserted, as well as a roll cage that was machined. So it's car shaped right now. We just have to put all the electrical components in and get it shipped to Rice. It's on its way here right now, actually. So our goal is to, as a first-year team, just compete, make it to the race. The design cycles are 2 years, so we plan to have this car for next year as well. Ideally, we have a lot of great Texas teams to target. UTD and UTA are also first-year teams, pretty close to us, which is pretty cool. And then UT Austin and Texas A&M are larger schools that we can learn a lot from. A certain Subaru stole that second car's name, so just kind of ignore the names. But our second car we hope to have completely designed and built by Rice. We used the molds from that Canadian team that helped us out earlier, just because a lot of us are freshmen and sophomores at the time, not knowing all the intricacies of aerodynamics. But by having this first car to learn from and reverse engineer all that process, we hope that future students can have that knowledge here at Rice and be one of the few schools that can do things like that and work with carbon fiber monocoque cars. So that would be for the 2028 and 2029 years. And then by then, it really takes 3 generations of car to become a state-of-the-art team. And so we're hoping to make it to that point eventually. We're kind of following in the footsteps of other Rice engineering clubs like our rocketry team that started around that same amount of time ago and are now pretty prominent clubs, especially with things like Austin and Brad's project going on. It's a really good time to be into engineering projects here at Rice. So narrowing into this year, we started in this semester with the revival of the Rice Electric Vehicle Club. We finalized an entirely new team structure, a bunch of club organizational and contractual things, getting set up, and then recruiting new members as well. And then just focusing on getting as much of that chassis finished as possible. The best piece of advice I've received is in terms of finding sponsorship is get something that resembles a car as soon as possible. Because once you have cool looking carbon fiber race car, it's a lot easier to be taken seriously. And then we have a bunch of technical reports that we submit to the competition as well. So a lot of that stuff's really important for safety reasons and getting to see what all the other teams are doing. And then getting started this next semester, this next week, actually, we'll be deciding a lot of the final decisions on our battery pack design, and then assembling all the mechanical parts into the finished chassis, which is being shipped to Rice right now. And then a bunch of different systems design things, and then hosting design reviews. So those are mandatory for the competition as well. We'll need to find like a faculty advisor that will be willing to review like the mechanical side of our car, an industry expert to review parts of it, as well as hosting design reviews internally with the team. So things like the mechanical team knows what the electrical team is doing and things like that. And then hopefully by the end of the semester, we have enough time to get, at least 100, hopefully, miles of testing. We don't have much road for that here nearby Rice, but we do have a nice little section of campus that hopefully we can drive on. We're a bit behind schedule, but hopefully that still can happen. And then the competition will be in July. So the second part, we'll talk about our car. So why we chose solar car, and a little bit about the competition and the problem. So looking at the different competitions, we thought solar car really aligned with Rice's strengths. We like energy and materials here. It also caters to us as a small school, favoring more interdisciplinary projects. We also considered there's other electric vehicle competitions as well. Formula SAE is by far the largest. There are these miniature formula cars in that top picture. The team formerly competed in Shell Eco Marathon, and we ended up settling on the Solar Car Challenge. Another big reason is the advancements in EVs, which I'm sure you guys are all pretty excited about too. Industry focuses right now are definitely efficiency, range is definitely a big thing, especially for larger cars. Battery chemistry is a big thing. Battery chemistry is what's enabling a lot of these lithium iron phosphate cars in China to just put down crazy amounts of power. If you've seen the car that bounces up and down on suspension in videos, the Yangwang U9 up there, it's one of my favorites. Materials and composites are another big thing. Another reason we put so much investment into that carbon fiber car. And there's even commercial solar cars available now, as we've seen with the Aptera. I consider having affordable EVs a performance application because I think it's enough of a design problem that the solutions we find here in designing our battery pack can directly affect commercial vehicles and make them more accessible for everyone. So for instance, our 5 kilowatt hour battery pack is small, but it might be similar to what like the Honda Civic Hybrid uses now, which is just the standard Honda Civic Hybrid is essentially an electric vehicle that is accessible to everyone, and it only uses an electric drive below 45 miles an hour. So we're already getting to the point where when we graduate and want to go work for automotive companies, we have a lot of the knowledge base that they're looking for. Hypercars and motorsports are another application. So like a hub motor we use would be very valuable in motorsports. And then even commercial solar vehicles are available now as well. Sustainability is the other big part of the niche we have. So energy storage is a huge problem, and we work a lot with that with battery pack design. Renewable energy is another big part. For us, it's essentially a competition restraint. So we have to adapt to changing conditions, and it makes the race more interesting. But it has practical implications in terms of the energy industry. So it gets to combine a little bit of interesting racing and student competition with training you for actually really meaningful careers as well. And then, of course, the material science as well as a lot of education. We get to take our car to different conferences and things like that. I know I would take my high school car to a lot of different places and show them to science fairs and things like that. And also training the next generation of engineers, business people, and just undergraduates in general, as well as proving and testing new tech. Tire compounds, battery cells, solar cells, sometimes certain materials like different coatings that they use, like thin film composites and things like that. A lot of those will be used on solar cars by industry partners for the very first time. So like the Bridgestone Ecopia is the tire compound they use for Priuses, a couple electric vehicles, things like that. And that compound is actually tested in like a thin profile slick tire that first races on solar race cars. So that's probably one of the biggest, I guess, industry impacts this competition has. And then as well as addressing some of the challenges of electrification of cars, weight and range being namely one of those that is really important to us as a design problem and directly affects the industry equivalents of our cars. So now talking about our car specifically, all right, does anyone have any questions over any of that stuff? Yeah.
You mentioned the chassis being delivered. So I guess you have a manufacturer that y'all are dealing with.
Well, we didn't have enough space to make it on campus. So we actually made it at over the summer at the Canadian school. We had their molds and just did a layup again on the same molds. So that's getting shipped here now. And then we had manufacturers machine the aluminum suspension for it, as well as a different manufacturer bend a roll cage for it. So just all the mechanical parts were machined outside of Rice. We tried to do last semester everything that couldn't be done on campus or that we didn't have enough space for. So a lot of that was like outsourced machinery or through other schools like UT Arlington and UIUC helped us with like our solar array because you have to get it laminated to your top shell. So just everything we didn't have room for at Rice, we tried to do last semester. And then the building of our battery pack and the things that can be done here will be done next semester. Yeah.
Any required photovoltaic output on your requirements on the vehicle, or is it as much energy as you can capture?
As much energy as you can capture. The limitation in the rules is 4 meters squared of area. Or sorry, 6 meters squared of area now. Our car was designed around 4 meters squared, and then they switched the rules to be 6 meters squared and smaller battery pack. So part of that transition from battery to solar energy that I was talking about. Our car was originally designed to compete in 2025 for our first year. So we were under that last rule set. And that's part of why we have the smaller car that's competing with the bigger cars now. Which I guess leads me perfectly into our chassis. So these are kind of our three, I guess, strengths if you compare us to a lot of the other first year teams. Having a pre-impregnated carbon fiber chassis is a big deal, essentially because it allows you to combine the body and the chassis into one uniform load-bearing structure versus the maybe steel tubes you would see in other student-designed cars. We also use the fiberglass molds. These were in Montreal with another team that we partnered with, and they enable really smooth aerodynamic design. And the car, because of that monocoque design, because of incorporating the body and the chassis into one structure, the entire car will weigh around 350 pounds empty, which is extremely lightweight for a car of that size, especially for something shaped like an airfoil. You have to be really careful with the aerodynamics there. As I mentioned, the design is a standard four-wheel car, which makes it pretty drivable, pretty approachable for first-time drivers. And it's split into two different halves. And then we did a lot of analysis in ANSYS was the main software used for that. CATIA, which is like the automotive specialized version of SolidWorks, was used to design a lot of the chassis. Then we used SolidWorks for, I guess, remaining parts. And then a couple like Altium for electrical design, couple other just standard engineering softwares. And then this is one of the kind of research areas we looked into. This was my personal project, is for, I guess, the battery pack structures and the crush zones are the main application of composite sandwich panels, which are structures you'll see in like airplane floors, things like that, where you have essentially a heavy thing sitting on top of a carbon fiber panel. And so what you'll have is carbon fiber face sheets on the top and bottom, and then some material in the middle, usually in like a honeycomb shape. And so for just a quick explanation of this example, what we tried is instead of just having one material in the middle, if you're switching from like aerospace to an automotive application, you also have to consider impact. So you want the thing to absorb lots of energy without just cracking, as you've seen in crush zones and automobiles and things like that. So what we experimented with was having two materials in that core. In the middle, a softer plastic called TPU, and then a harsher plastic called PLA. and the outside, on the outer edges of that. Both can be 3D printed quite easily. And you can see there in that green graph, the area under the curve is all of the energy that's absorbed. And we were actually able to find that our crazy idea did work, and it can, oh. Yeah, sorry. Yeah, so I'll restart that. But we essentially found that we can actually increase the amount of energy absorbed by our carbon fiber by introducing another material to it. So that's just one of the research applications that we do on the mechanical side through our chassis. Next, the battery. Yeah. If it like plastically deforms, yes. The idea mainly is for like our design report validation. Yeah, I say it in the bullet point. We have to prove it'll survive 5G impacts. So that hasn't happened recently, but in the case that it did, we would want as much energy as possible to be absorbed by the different structures for safety reasons. And then also exploring, like, it'd be pretty cool if something like that made its way to commercial vehicles as well. And then the batteries are next kind of biggest strength to optimize. Our current design, just using a couple of cheaply available cells, 266 21700 cells. The pack weighs 20 kilograms total. Pretty low voltage, just around 140 volts nominal, and 5.25 maximum kilowatt hour capacity. Our design is a little bit below that, just to be safe, so the judges don't have any problems with it. We got to that by using 38 cells in series and 7 in parallel. And then for safety reasons and for BMS reasons, it's split into 4 modules. So each one has a voltage below 45 volts, so it's safe to handle. And then the BMS combines them all into one system. The things to optimize there are energy density, and more importantly, that we've become aware of throughout this process is DC resistance as well. So that 30 milliohms is referring to each cell individually. Oh, and the 300 watt hours per kilogram is actually a different design that I'll get to in a second. So that depends on the chemistry. So the first one that we did our main original design last semester around uses just a readily available Samsung 58E cell. So this is an NMC cell, which is pretty typical of what you would see in the Model S and in the Model 3 before they switched to lithium iron phosphate. But we also, like in talking with industry partners and things like that, are considering working with a company called Amprius based in California, which uses silicon anode cells. And so they're the ones that have the 300 watt hours per kilogram energy density, which is about twice the energy density of the typical NMC cells. So how I mentioned the NMC cell is 20 kilograms in weight. If we do go through with the silicon anode cells, that pack would only weigh 16 kilograms, which doesn't sound, 4 kilograms doesn't sound like a huge difference, but proportionally, that difference is really huge. And imagine that scaled to the kind of battery pack size you would see in a commercial EV, where like these silicon anode technologies would make a huge difference. And we are waiting to make a final decision because CES is actually going on right now. And we're talking to Amprius to see if we could get 21700 cells as opposed to 18650s. And we'll make a decision on that this week. So exciting time for battery stuff. We also considered lithium iron phosphate just because for safety reasons, it's safer than NMC cells. They don't have thermal runaway like NMC do. So if you've seen like if one cell gets discharged too much in an NMC pack, it'll cause a fire and it'll destabilize all of the cells, kind of cascade through the entire pack, where lithium iron phosphate are much more resistant to that. You could pretty much like drop a lithium iron phosphate cell and run over it with your solar car and it would be fine. So we considered it for safety reasons, and then also because it's the cell technology behind like these super high performance EVs nowadays. The energy density is worse though. So it's worse for efficiency, better for power, which is why we are leaning towards the NMC cells now. And then electrically, this is just a basic electrical schematic that we use for preliminary design. You have your high voltage battery pack that drives your, that essentially drives the car. And that's the thing that is controlled by the rules. They seal it with like FBI evidence tape. You can't charge it. But then we also have a whole bunch of low voltage systems that are powered by a 12-volt battery, just like a normal car would have. So we have turn signals, headlights, and then a whole bunch of telemetry data that send things to our strategy team. So kind of just following the power across this diagram, the solar panels will then charge the battery pack, which is then split into 4 or 5 modules, depending on which cell type we go with. And then from there, that's what drives the motor. It goes to the inverter and then to the motor, which leads us to the motor. The motor is one of our biggest advantages and is typically the most important thing to a solar car team. It's the most expensive component, the most high tech. 98.3% drivetrain efficiency is the reason why. So having so it's extremely lightweight. Motors are usually a very big contributor to why electric vehicles are so heavy. So minimizing that is extremely important. We do that through a hub motor. So another thing the EVAN people would probably appreciate is we don't have any drive axles at all because the motor and the wheel hub are integrated and we just have that one wheel being driven or 2 wheels if we had 2 motors. So ours was custom made for our car, meaning we could choose like the all the hub specs. We could choose the gear ratio. And it was essentially designed for a car of our weight with a top speed for the American Solar Car Challenge. Total efficiency of 98.3 is really good for a drivetrain, and our inverter is 99 point something. So a lot of this energy from the battery is actually getting to the wheels and driving the car, which is a huge advantage of this kind of technology. Yeah. Well, it's a 3-phase motor. It's a brushless DC motor. Yeah. Are any other questions on the car part of it? Yeah. If you don't get it sponsored, it's $25,000. That's just essentially because it's a hub motor and all the aluminum machining that goes into it. It's also shipped from Australia. It's an Australian company that assembles these. It's essentially a duopoly on electric vehicle solar hub motors. There's a company in Japan called Mitsuba, and then this Australian company, Morand, that will design the custom motors for you. And they're both around, 20 something $1,000. Though if you have a cousin in Japan, it might be cheaper.
I have a question.
Yeah.
Does this motor integrate or enable regenerative braking?
Yes, it does. And so that's also handled through the inverter as well. You don't use, it depends on the track, how much you actually use regenerative braking. So like we also have 2 traditional braking systems, calipers as well, or 2 master cylinders and then calipers in the front and the rear for standard brakes. The brake pedal in the car only controls those hydraulic brakes. So the regenerative braking would be controlled through a setting on the steering wheel. And it essentially works in like a 1-pedal driving mode, where if they lift off, that switch on the steering wheel controls how strong the 1-pedal driving is.
Do you have calipers on both sides this time?
Yes, we do. Yeah, so we part of the rules is you have to have 2 redundant hydraulic braking systems. The way we do that is we actually just have a front and a rear brake system. So obviously your front brakes do more work, but we also have the ability to have 4 brake calipers across the car, which in theory could be used to, I guess, maneuver and turn the car as well. But it's just standard hydraulics with no electronics for now. Yeah.
So a question on the chassis aerodynamics. Have you considered something like what the Chaparral guys did umpteen years ago, active elements that would allow you to reduce the downforce when you're going in a straight line and only have it at full downforce when you're trying to maneuver braking or turning?
Yes. So essentially, it doesn't work for weight because weight ends up being a bigger cost than that. You could theoretically on the track race, what most teams just optimize for is the cross country race where you're just driving in straight lines and downforce isn't important. If you were optimizing for the track race, you could though. And it's definitely a more cool. We've also thought about maybe incorporating some downforce into our car, like maybe an aero kit, like a spoiler or something to add to the back of it. The cars are essentially designed around having no lift or downforce at all, because lift and downforce come from trading drag, and we want drag to be zero, or not zero, but we want lift and downforce to be zero so the drag can be as low as possible.
I have one question. What is the weight of that brake rotor? It's a beautiful design and looks very minimal material.
I don't actually know. It's a lot of teams actually do use bicycle parts for some of these. So that's our rear suspension there. That's where the motor would go. And so it's just swing arm suspension. Just because of the packaging constraints there, it's not a full double wishbone suspension like in the front or like you would see in a commercial car. So it's pretty similar to bicycle suspension actually. Yeah.
So when you said it's a custom MRAN design, did they give you like how custom could you guys get? Was it like ability to change the magnets or change the diameters of the wires, or did they say you have certain constraints, we could change it for certain speeds, or like how much customization did you get?
Really, we just changed the gear ratio on the hub design, and then we copied the Canadian team's design exactly for everything else. So we would potentially be able to customize, or I don't even know what you can customize in terms of the magnet design. I'll find something. I'll find they have a presentation about it that I can pull up afterwards about the motor. You can change things about the winding, but I don't know if that would qualify as a different product or not. Yeah. So kind of our next steps on what's remaining with the car. To get it finished, the parts we're still missing include wheel and tire package. The main thing being because the tire compound is such a industry specific thing. Pretty much just Bridgestone and Michelin make the tire compounds we need, especially at the low profile we're looking for. And then the wheel is kind of designed around that. The car is designed around having a 16-inch diameter wheel. So hopefully being able to find a tire with the right profile to fit in the car as well. And then waiting on that battery chemistry decision to order the rest of our battery parts to assemble that high voltage battery. And then integrating all of the remaining mechanical parts like the seat and then the electrical components with the battery pack and inverter and motor into that chassis so it can be drivable. And then for the competition, there's a lot of logistics that go into getting the car to the track, making sure we have enough testing. It's kind of a mandatory tradition in solar car to drive your solar car through a drive-through when it's finished, and have take it to Cane's and have the person reach all the way down to hand you your box combo. Yeah, not much space to put that box combo though, but you do have mandatory cup holders or one mandatory cup holder through the rules, so at least we have that. And then a bunch of technical reports. We just submitted our first couple preliminary ones, one mechanical, one electrical, and then they'll ask for some more in-depth ones that are due at the end of the month. And then insurance, registration, things like that. And then starting to focus on the rest of the team outside of the technical stuff with the media and marketing, and hopefully finding industry connections to keep this project going for our next generation. And then the other big part of this semester will be the strategy. So you can see in the top right, that's the data I used in high school for my car. That's what the people sitting in the strategy tent will be looking at. And then the driver will have access to essentially just the live data points for that. So they'll see what their live speed is, what their live motor power or current is, what their solar array production is in watts, and then what their battery voltage is. The race essentially works that you want to finish the race with exactly 0 energy left in your battery. Because if you have more, you could have gone faster. And then if you end up draining your battery, it takes a lot longer to get the car started up again than to charge it when it was still running. So telemetry and data analytics become pretty huge as we get the car into a place where it's ready to be tested. We'll have a pit crew and a race crew decide who wants to actually go to this competition and hopefully can get time off from internships in the summer to attend. And then deciding what we want our strategy to be, as well as driving the car as much as possible. Hopefully, we're able to find some places on campus like the inner loop that goes around Rice, some low traffic areas to do some preliminary testing. So it's going to be an exciting competition this year for sure. It's growing pretty fast. The competition was pretty big in the 90s and early 2000s. Back then, it was sponsored by General Motors. When they pulled out, it got a bit smaller. They made the cars a lot smaller, just for safety reasons, because you had these 90s kids driving their 80-mile-per-hour solar cars that were very airfoil shaped at the time compared to the designs now. So now we've kind of made it full circle, gone back to those bigger cars, but with a lot more aerodynamic knowledge in hand. And the bigger cars, this look a lot like this one in the bottom right here. This is the team that won the International Challenge this past summer. They'll be coming to the American Challenge this summer. So technically they're one of the 7 new teams, but we'll be hoping to learn a lot from them. You can actually see it, the kind of gimmick in the International Challenge is having an airfoil sail type thing on the top of your car, because in Australia, there's enough side wind that you can actually get propulsion from having an airfoil on the top of your car. So I'll be interested to see if they still have that for the United States, if that's still worth the weight penalty or not. But that's an interesting little feature of those cars. That car is also a 3-wheel design. So another big pro of this competition, I think, is you see a lot of different designs. So you have 3-wheeled cars, 4-wheeled cars. You have these bullet-shaped, long, skinny cars. You have our car that's more, car proportioned at least. And then a whole bunch of other things. Some teams try and not have this canopy shape at all, and they have the solar array above the whole thing and the driver sitting under it. So there's a whole bunch of different strategies you can do here, and the competition really rewards trying out different things, especially aerodynamically. And it'll be our first solar car challenge, so we hope to, I guess, learn a lot. There's a lot of things that you find out just racing for the first time, and getting to try out your strategy against others. Definitely my favorite competition would be once we had access to all this data, it really informed race strategy. The year after, with this kind of data in hand, it came down to a really tight race for my team. And probably my favorite story is it was down to like the last 45 minutes of the race. We were within a lap of the team behind us, and we realized they were on, like, we were essentially on one half of the speedway and they were on the parallel other half. And so we would try and speed up to lap them and get the advantage, but then they would also speed up. At the end of the race, though, we had a theory that maybe their telemetry had gone out. And so we tried having our driver slow down, and their driver also slowed down. And the reason they were on the other side of the track is just to keep out of view of our driver so they didn't catch on to us. So once we figured that out, if you've ever seen Formula One and how the teams will kind of wait for like a yellow flag or something to happen to do their pit stops and their crazy strategy decisions, it was a lot like that. It was a very hot day, and we had a feeling that there might be a heat warning or something in effect. And so once the competition made an announcement about like a potential heat warning or a heat advisory, so essentially make sure your teams all have water or things like that, we faked that we were panicking and we floored it in our car to pretend that we thought the race was going to be canceled early. And their driver didn't think through that and also floored it in their car. And within like 30 seconds, their car died on the track just from the over voltage of that. And so that's how we won that competition, is just by that strategy. So hopefully a lot of fun stories like that will be happening at Rice pretty soon. And it's really enabled by all of this cool engineering and data and strategy and passion for EVs all coming together at the same time. So another part is how we're being involved in the community. A big part of our team is that we are open to all majors, all students, and we hope to have different levels of involvement for each of the people that are interested in. We have a course that students can enroll into on the electrical sub-team to integrate with their academics, kind of apply what they're learning and maybe receive some more special instruction in things like motors or power electronics. And we're looking to also get a similar course for mechanical engineers as well. And then unveil our final car in April at the end of the year. And then another big aspect is how involved we are with like other automotive enthusiasts, EV enthusiasts, and other teams, especially in Texas, now that there's 5 teams in Texas. We've been talking about a potential Texas teams mock race. Our car might not be finished for that, but we'd love to be there and I guess support UT Austin and Texas A&M. Learning from industry experts as well. Lots of cool people show up to these kinds of things and help out. The competition, now that it's not sponsored by General Motors, is entirely made up of volunteers. So a lot of people are really passionate about this kind of racing and this kind of education. Another big place to take your car and get some cool reactions is car meets. So we'll probably do some things like that, and hopefully be able to drive it to different places. We don't have a person with a trailer or a truck, which usually makes these things a lot more convenient. But we still hope to be pretty involved in the community once we get our car in a presentable position. Actually, it might. It might. So Brad, keep in mind the 4 meters by whatever it was. 4 meters by 1.5 meters, just in case. So yeah. It could charge it. I bet they. Yeah. Not during competition, but yeah. Before competition, before the evidence tape seals the battery. You're actually allowed to start the competition with a full battery, but once the race starts, like that's when teams go all hardcore, and like as soon as you cross the track lines, like a lot of teams will forbid their driver from driving at all, and you have to like go send your freshman to go push the car and stuff like that. We're not that serious yet, but it definitely gets there at some point. So yeah, that's everything I have. Definitely keep in touch with us. We're launching a website soon. We have an Instagram, and then I've included my email there as well in case you have any questions for me. And if you have any questions right now, I'd love to answer them.
All right, that's fantastic, Sebastian. So yes.
So I'm Gary Woods. I teach the course that Sebastian talked about, and I'm the faculty sponsor for the REV team. I just want to say one of the things we're doing in the spring is building our battery, and I would like to be educated about how one makes a battery and how one keeps it safe. So if anyone has any expertise, I'd love to chat with you after this.
All right, yeah, we'll count on folks here.
I'm curious about the metric miles per kilowatt hour for these cars. It's probably 20 or something like that.
I don't know. We'll have to do testing for that, because when your motor is so efficient, the limit is a lot of like rolling resistance things that come down to your tires and to your hubs, and we really won't know that until we've actually driven the car. I could probably find you that data from another team though. It might be available online.
We hope to have good interaction between your Rev and the Houston Club. I mean,
Yeah.
absolutely ongoing.
Yeah.
Yeah. So
Historically, though, is there like a number?
Historically, are there numbers that just a guide of what these cars use per mile?
I just don't know. I don't know per mile, but what I would do is like we would know at the end of the race results, you could get like 900 miles across. You could find a team did 900 miles. A lot of teams will like post on their websites how much energy they used to cross that race, and so you could just divide those two. That would, yeah.
Are you guys going to calculate that at all into EMPG? Because that's probably well in the thousands at 5 kilowatt battery capacity.
We probably could. That would be on our strategy team this year. We really do need testing data to do that, but yeah. Because right now the only thing we know is drag. That's the only thing that we do know, but all of the rolling resistance stuff is kind of just at the mercy of our mechanical tolerances right now. Yes, that's one of the solar cars, right?
Okay, yeah, so it's SunSwift 7 Australia that I think you were mentioning, and so they got 26.3 miles per kilowatt hour.
Okay.
Good
Yeah.
numbers to know. And by the way, I'd like to mention to folks here, encourage the students, Omar is going to be our speaker in a couple of months, and so we'll all get to ask him questions then.
I do have one other question for you. Did you guys, with the motor, did you break it, tinker down to the flux field of the magnets at all for efficiency gains?
Not yet. So we kind of trust the professionals to do that for us when we're paying a bunch of money for it. Some teams have tried to build their own motors. So you mentioned SunSwift, so like Western Sydney, some of the Australian teams, maybe some of the European teams have looked into it. Teams like Georgia Tech have started building their own motor inverters, things like that. So kind of going back to like our timeline of having, this is just our first car, there's a lot of commercial parts in it. But as we get on to, I guess later, we'll have more and more of those replaced with student design parts. And hopefully like maybe a senior design team or something like that to kind of start filling that in. But kind of reverse engineering that commercial product for now and then eventually getting there.
It seems that at the race level, the strategy is very important. Are you going to implement some AI at some point?
Yeah,
Or is it allowed by the rules? Or
Honestly,
that's a secret sauce.
Honestly, to some extent, yes, because there's a network of so many complicated variables going on. The problem is the data you rely on to make those decisions is not very good. So like if you're making your whole strategy around solar irradiance, just the weather predictions are not very accurate. And so that could be where machine learning is helpful in that you need to respond to live conditions like very fast. So that's probably where we'd look into it most. It's just finding out how important each factor is, how important the temperature is. So like that's another aspect is like keeping your array cool. Some teams will have like water misters on their car that spray their array to keep it cool, things like that. So finding out how important each of the different like environmental variables to respond to is. At the moment, we haven't really looked into it much since the strategy team is like just getting started this semester. But definitely open to it. And as we mentioned that this car's also competing in 2027, I think that's where a lot of the optimization comes into play.
Good. So.
Did I pull it out?
That's close.
Oh, close one. Oh, you were talking about drag and all that other stuff. If I remember correctly, you said Michelin supplying your tires, or you had a couple of people.
My understanding is that Michelin only does custom orders if we're able to find whoever does that. And then Bridgestone makes the Acopia tire, which would be the compound we'd ideally be able to get.
Okay, I was wondering if they were going to supply different various compounding stuff like that. Are y'all planning on doing any research on that, and as far as tread pattern and all that other
So
stuff?
we'd have slicks with no tread at all. So like obviously the commercial version of the Acopia has different tread patterns and things like that. If there's too much rain on track, which there usually never is, but if there was, they probably just cancel the race. So we would worry about that if we were doing lots of like testing on road. And even when you're testing on road, you typically have a trailer vehicle with you. And so a lot of the times, if you're in adverse conditions and it's not safe to drive, you have the freedom to just not drive and to trailer your car. So that kind of simplifies a lot of the tread wear designs. Some teams do use different tread on their tires, but for us, we're not at that point yet.
I'm curious what happened with where your high school car is. What it's doing.
So my high school car, it essentially got parted out, and the team is building a different car. So my high school, the high school itself didn't really do much with us. So we just decided to accept members from other high schools and kind of separated from the school. So they're off doing their own thing right now, probably having a new car. My car, its motor is actually the UT Arlington motor now. So they hopped on it before I did, apparently. So yeah, it's the Japanese company, Mitsuba, that motor. That one was pretty cool. It had to be repaired because I might have been in the car when it stopped working. But at least I know how not to do that now that I've gone through and procured a different motor. So yeah, I believe UT Arlington might also have the battery pack from my high school car, but those are of a bigger size than the college ones are. So I'm not sure what they'll do with it.
So if there were an incendiary event, is the driver totally separated from the side where all the electronics and batteries are located?
Yeah, so that's the benefit of our side is the right side is the battery pack. And so they have the physical separation there. And then they also have like entire like relay disconnects they press to completely disengage. There's one for the battery itself. It's a disconnect right by the battery, and then there's one by the array.
Nothing.
So the procedure is to hit both of those, throw the canopy over you, and jump out of the car. That's part of the scrutineering process I mentioned, where they kind of grill you about your car. Is you actually have to, for every driver you get certified, they have to do a mock fire event, and they have to prove that they can shut down the car and jump out of the car within 15 seconds. And part of that is they actually, if you forget to fully disconnect everything and turn the car off, you fail that test too. So.
Okay. Yeah.
As I remember correctly, you used, as I remembered correctly, you used 5 kilowatt hour battery system, right? And is this the kind of ideal battery capacity for your car, or was there kind of some limitation for weight, or
So
why you choose the 5 kilowatt hour? Yeah.
No, so now the regulation restriction is 5.25 kilowatt hours. And so our design was just to get as close to that number as we could. And so with the 38 Series 7 parallel, it works out to 5.16 kilowatt hours, and that's just as close as we could get to 5.25.
Right. So if you use a lithium phosphate, then you could have like a more weight, and it could affect the size of the capacity or something for your decision, right?
So yeah, the restriction is now capacity. It used to be weight. So it used to be when we were designing it for the 2025 competition, it used to be that they allow you like 30 kilograms of weight. It actually depended on your battery chemistry, depending on which one, you get a certain amount of weight, and then you fit the maximum capacity you can into that. They switched away from that because it heavily advantaged more resourced teams that could get like these silicon batteries and things like that, that pretty much just double your like specific energy. And so you just really can't compete with that as much as you can, where if the limit is just a 5.25 kilowatt hour battery, you see ours is 20 kilograms. And so, you know, even Michigan with their $2 million budget is still going to have a 15 kilogram battery. And so it kind of, they still get an advantage, but the playing field's more even, to where if we have a better strategy than Michigan, we still have a chance at winning.
I have a couple of questions about the race itself. What is the average period of time from start to finish? And is it all a road course where you're going hundreds of miles?
So the track race is the one we're targeting now, and that's the qualifier to the road race. And so the track race is 3 days, 8 hours long, and then a 30-minute mandatory lunch break somewhere in there. So that's part of strategy, is when you take that lunch break. Some people will do it at the very end of the day. And then the other race, they try and avoid interstates and high speed roads. Typically on track, your average speed is in the 40 miles per hour, and on roads it'll be near 60. And so they try and pick the roads accordingly with that.
And they're both done by the same outfit, American Solar?
Yes.
Okay.
So technically the track race is called Formula Sun Grand Prix, but it's still part of the American Solar Challenge.
Okay.
The reason they're separate actually is because the cross-country race is only on even years, while the track race is every year. And then the reason for that is that on odd years, the best teams go to the international cross-country race in Australia.
And one other question. What all is liquid cooled? Are the motors and the battery and all inverter all liquid cooled?
No, they're all air cooled passively, just giant heat sink on the inverter. And then you have to have a certain volume of air has to be moved through the battery pack according to the rules. And so we just make sure that so like another ANSYS simulation to figure out how hot the batteries get, and then how much spacing you need between the batteries for them to actually cool effectively. And then that's how we ended up we switched from like a flat kind of traditional battery pack design to this 2-layer design. And then part of that is more surface area for ventilation to get through those fans. Yeah, or they regulate the minimum of your fan specs is how they check it too. So you have to provide like data sheets for all your cooling systems.
When you build your battery pack, are you going to attempt to measure the capacity of each cell and get a balance set?
Yeah.
Or maybe does the BMS take care of balancing as you're going down the road?
So the BMS takes care of the charge balance between them. So each module of the 4 has its own cell management unit that kind of takes each row in parallel and balances across the rows in parallel. Then you have the modules themselves are all controlled by the BMS, and then that's what takes the power out, sends it to the inverter. As far as measuring the cells, though, we do measure their capacity. And we try and arrange it so that each row in parallel has as close to the same capacity as possible, because then they'll discharge together and not like naturally tend towards being unbalanced. And so we'll have 500 cells we order, and then we use 266, or if we do the 18650s, like 300 something. So that way we have a lot of margin to get rid of the cells that don't match well together for safety.
So clarifying on the battery design, you're running 4 parallel strings. Is that right?
No. So in total, it's 7 parallel strings. And the 4 modules are split. So that way it would be 38 divided by 4 in series. So each module has 7 in parallel, And then
so-
what the
so
modules
ultimately
are
it's
is
38 in series.
Yeah. So each of the 4 modules connect in series. Yeah.
Thanks.
Okay, well, we've really gone way over time and everything.
Sorry about
It's
that.
so much fun that
Yeah.
I'd like to thank again Brad and Austin and Sebastian.
Yeah. Thank you guys for coming to Rice.
And as I said, I hope we're going to have a lot more interaction here. We have our monthly meetings, and except for December when we have our social. And so you're always welcome. Everyone's welcome, either in person or online. All the other students who are, and we'd love to be back here. Good. Yeah. Yeah. So coming back here again would be great. Great. Yeah. Yeah. So, all righty. Good. So thanks to the folks online and everything, and we'll end the meeting with that. Thank you.
Say goodbye. Hi there.